Hi everybody, I'm Olivier Regnier-Coudert from Airbus AI Research, and I'm going to present some work done with my colleague Guillaume Povéda on an empirical evaluation of permutation-based policies for stochastic RCPSP. First of all, let me present a well-known resource constraint scheduling problem, which is a widely studied scheduling problem where we have activities to schedule, here 8 of them, under two types of constraints. Precedence constraints, meaning that tasks can only be started if all their predecessors have been completed, and resource constraints, where each resource type has a capacity that needs to be respected at each point in time. And note that the resource need is specific to individual tasks. The objective is to provide start times to all activities, such that all the constraints are respected and that the makespan is minimized. Now, in this paper, we focus on a variant of the RCPSP where the duration is stochastic. In this variant, the exact duration of each task is unknown, but the distribution is known. And you can see on the illustration that the duration delta is now drawn from a distribution. And in this illustration, it is a normal distribution. The approach that we present in the paper can be used with any type of distribution, although our experiments are based on a uniform distribution. Also note that the approach is in principle suitable for other sources of uncertainty, such as resource availability, resource needs, or even uncertain task arrival. In our work, we speak about scheduling policies, a term that we use in the context of uncertain environments. In an uncertain environment, unexpected events can occur at execution, making an initial potentially optimal schedule no longer valid. So for example, a task taking longer than expected may result in some conflict in a very tight schedule. So we believe there are three main approaches to handle this. First, we can simply re-optimize the schedule each time something changes in the environment. The issue is if we do that, is that it may need to be done often and that it may require a lot of compute. The second approach would be to repair the original sheet's updated environment. So while this is often done in practice, it can also be challenging, especially when there are a lot of conflicts to solve. And finally, we can also think of using a policy rather than a fixed schedule. So the term policy is borrowed from the MDP community and refers to a lightweight procedure that can associate a feasible action given a state. So in our scheduling environment, a state is defined by several attributes, such as the current time, the status of a task, the start and end times for some of them, the progress of the task, and the sample durations. And we also have some information related to the resource usage that is also contained in the state. And in terms of actions, we can have actions of two types, either starting a task or progressing in time. With this principle, we can move from states to states by applying consecutive start actions before eventually progressing in time. And this is what you can see in the illustration below, where the tasks 8 and 5 are started at time t. This is the task 8 being started here. We go to a new state, which has the same current time t. Then we start a task 5. We end up in another state with still the same current time. And then we apply an action of type progress, and then we move on time without starting new tasks. At the core of our algorithms is a well-known mechanism called SGS, standing for Schedule Generation Scheme. It's a greedy procedure that generates a feasible schedule based on the environment information, so what we have in our scheduling state, and also based on an input permutation. The schedule produced is feasible in the sense that all the tasks have a starting date and that the resource capacity constraints are respected. So without entering in the details of SGS, it's still important to understand that the SGS procedure constructs a schedule by inserting at the earliest the task in the order they come in the input permutation. So tasks at low indices in the permutation will have a higher priority than tasks placed at the higher indices. Of course, because SGS handles the resource capacity and precedence constraints, there is no guarantee that a task placed before another is started earlier. So because SGS always produces a feasible solution, we can create scheduling policies around it. But for this, we need a strategy around the input permutation, or the task ordering. First, we can use a fixed permutation. And in this work, we have generated a representative instance with average duration and solved it with constraint programming. From the optimized schedule that we've obtained, we've created a permutation by simply listing the task by starting times. We then store this permutation and use it whenever SGS is called. We call this algorithm Cpsgs because we solve a problem with Cp and then run SGS on the resulting permutation. The obvious limitation with this policy is that the permutation is learned once, and we can imagine that in some cases where the environment has become significantly different from the representative instance, this permutation may be far from optimal. Here is an overview of Cpsgs, where we solve offline the RCP instance using Cp to obtain a schedule. This schedule is then converted to a task permutation pi, and at execution, and starting from an initial state S0, SGS will be called using the state information and using the permutation pi. SGS will produce a schedule from which we'll extract the next action, which will bring us to the new state, S1. And we'll do this several times to progress in time and to progress in our schedule. But note that the task permutation remains the same each time we call SGS. For the second policy we have looked at, we do not learn a permutation offline. Instead, we learn a heuristic that can be used to generate a permutation when needed. This approach is based on the use of genetic programming, and it's called GPHH, standing for Genetic Programming Hyperheuristic. Heuristic takes as input a set of task features that are calculated at current time, and it produces a priority level for that task. And once a priority level is calculated for each task, a permutation can be derived. Because some features use state information, the priority level can change from a state to another, making the resulting permutation dynamic, and hopefully reflecting changes in the environment. Also note that the rules are generic and not bound to a single instance, and that makes GPHH heuristics potentially transferable between RCPSP instances. So we now see that GPHH is using several RCPSP training instances to evolve a heuristic. And at execution, like for Cpsgs, the SGS algorithm will be called to generate an action, here or there, to move from a state to another. But this time, the permutation that will be used as input to SGS will be obtained for each state by using the stored heuristic. So you see, for example, that pi0, the permutation to be used at state S0, will be generated using the state information contained in S0, the GPHH evolved rule to get this. And this is what will be fed to SGS to get the action. And we see that it may change from a state to another. In terms of features that can be used in a heuristic, we have three main categories. First, some features related to the time, like the task duration or earliest possible start, for example. We also have features related to the precedence graph, like the number of successors or the number of predecessors of a given task. And finally, we have features related to the resources, like the total number of resource units required by a task, or the number of distinct resource types, for example. All features are normalized in order to ensure generalization of the heuristics. And finally, we have restricted ourselves to the use of those 7 basic operators to combine those features. And you see here an example of a heuristic and how permutation is generated from it. And in that example, we have 5 tasks, A1 to A5, and for each, we calculate the 3 features that are used in the heuristics. So you see the 3 features are the latest finish date, LFD, the total number of resources, and the number of predecessors. And for each of the tasks, we're going to compute the value of those features. And based on the heuristics, we're going to compute the priority level alpha I, which are given here, for each of the tasks. And so alpha is a result of this operation using those features. Once we have the priority level, we sort those in descending order to get the permutation pi, which you have here. And in that example, we have the permutation 34021, which is the one corresponding to that particular state. Now, let's imagine that at the next state, we observe a duration change for the task A1. We can now recompute the feature and the priority levels and update pi. So a change in A1 on its duration means that the latest finish date might be different. In that case, it's been reduced. And so we have a new priority level, which is here. And when we look at the permutation, which is resulting from the priority levels, we see that 3 indices have changed in comparison with the permutation used in the previous state. So we see that it reflects the changes in the environment. To evaluate the potential of GPHH, we've taken 30 classic RCPSP instances from the PSP lib library, and we made them stochastics by replacing the original task durations by uniform distributions centered around the original durations. For the comparisons, 1,500 execution scenarios were generated, and they were kept hidden from the solver. In terms of algorithms, we looked at 4 methods: random walk as a sanity check, a published handwritten heuristics called MDPR that prioritizes tasks that unlock the most tasks when completed. And of course, we included Cpsgs and GPHH in the comparisons. And we used a very standard GP implementation with a population of 40 and 100 generations, and the remaining settings that you see on the right-hand side in this box. Finally, we've also solved optimally each execution scenario using CP in order to obtain lower bounds. And using those lower bounds, we can understand how far from optimality the different policies are. And so the comparison is mostly based on the distance of the 4 other algorithms to this lower bound. So all results we present now are based on the execution of the shading policies on the 1,500 test scenarios. This first table shows the relative difference between pairs of algorithms. And the first thing we observe is that using GPHH over Cpsgs gives significant benefits on all problem dimensions. And the main message behind this is that updating the permutation given to SGS is associated with a gain in performance at execution. The second observation is that although GPHH is significantly better than the handwritten reference heuristic on all the problems, significance is not reached all the time when we look at problem dimensions individually. We see, for example, that for J60 and J120, we don't reach a statistical difference. However, we see that to be competitive with MDPR, SGS policies require update of the permutation because Cpsgs does not outperform MDPR on any problem family. If we look closely at the distribution of the makespans obtained by GPHH and Cpsgs, and if we abstract the runs that have reached the lower bound, we see that the distribution is more skewed towards the lower bound for GPHH than it is for Cpsgs. And this confirms the previous trend. And finally, we look at the number of runs on which the different algorithms have reached the lower bound, so out of 1,500 scenarios, with, again, GPHH being optimal at execution more often than the other 2 policies, although this is a small difference. So we have 13% of the runs for GPHH reaching optimality against 11% and 10% for the other 2. Right. To conclude, we have evaluated the concept of SGS-based policies and concluded that GPHH has a good potential. Yet there is still a lot that can be done to better understand what it can achieve and to improve it. So since the paper was published, we have added a complexity objective and used non-dominated sorted selection in order to reduce the complexity of the heuristics from 80 operations to heuristics that are much more readable with something around 10 operations. Another issue we have is linked to occasional unreliable heuristics evolved by GPHH. And to illustrate this, we show in this table the results of 50 runs of GPHH. So that's 50 different heuristics that are then executed on the same scenario. And we see that we get a low makespan, which is equal to 69, and we get this low makespan on using 48 heuristics. But 2 out of those 50 heuristics give very bad results with makespans of 87 and 98, respectively. So among the ideas we have to solve this is the use of ensembles of heuristics to try to reduce the impact of outlier heuristics. Also, there is a lot to do around analyzing the impact of the properties of the training instances that are fed to GPHH, and especially in order to understand the trade-off between genericity and specificity of the evolved heuristic. And finally, the last issue with this approach is that it fully relies on having an SGS-like algorithm. This is not an issue when we're speaking about the standard RCPSP, but it is something that is challenging in real applications where some specific constraints can be hard to encode in a procedure like SGS. That's the end of our presentation. Thanks for listening, and we'll be here to answer questions. Thank you.